because Adam just discovered a fatal flaw in his thesis and was conscious, but that is not the case. Everything is right on track. This is the final exam for Adam Campbell, and if you're here for a Philosophy 101 class, it's that you're in the wrong place. Anyway, the format is going to be Adam's going to talk to us for, what, 45 minutes or so?
That's about right.
Explain his research during his PhD program. Then we'll have a time for questions from the floor, after which we'll move into a closed session with the supervisory committee. I'll tell you a bit about Adam. Adam is a degree collector. He has a Bachelor of Science in Physics from Oregon State in 2003. A Bachelor of Science in Geology from Portland State University in 2006. He has a master's degree from Portland State University in 2009, where he did glacier flow modeling of Crane Glacier following the collapse of the Larsen B ice shelf. And now he is hoping that he'll get a Ph.D. from University of Washington here in 2015. Anyway, I want to tell you a few things about Adam. He gave me something called a distilled CV. So I'm not quite sure what that is inferring anyway. But among other things, notice on his awards from Portland State University, he got the Stout Scholar Award. Also, he's widely recognized throughout the department. In 2010, he got the best geobiology poster in our department at the ESS Gala. So he's not just a glaciologist here. He also has some other distinct honors, and he's been on our college creation committee. And again, I didn't dig too deeply into that, what that was all about. He's the president of Engage Science here at University for outreach, and he's the regional steward for the United Auto Workers Local 4121, which means he has a job opportunity. If he doesn't like science after a while, he can go to Detroit. Anyway, so that's Adam. And Adam,
all right.
about your research.
All right. Thank you, Ed, for that kind introduction. I really appreciate it. So today, I'm going to talk about Snowball Earth. Specifically, where could photosynthetic life exist on this environment? So I'm going to take a play out of the TJ Fudge playbook, who cannot be here today, and do my acknowledgements before my talk. So I'd like to thank the members of my committee, Ed Waddington and Steve Warren, for co-advising me through this long PhD that I've had here. And then also for Dale Weinbrenner, CC Bitts serving on my committee, and Luann Thompson serving as my GSR. I'd also like to thank my family and my girlfriend Janet for all who traveled here today to be at this exciting event. It's good to see some friendly faces in the crowd. I also would like to acknowledge the many of you that I've gotten to know and be friends with during my time here at the University of Washington and ESS. I've made some amazing friendships over the years, and because I've made so many friendships, I couldn't leave my friends to just one slide. I had to provide extra slides here to acknowledge all of my friends in Seattle and everyone. And I'm really going to miss the roof beers that we've enjoyed many times and on many occasions. So thank you all for being here. But now I want to talk to you about the Snowball Earth hypothesis. So let me explain a little bit about what is Snowball Earth. So we have evidence that there were glaciers near sea level, or at sea level near the equator in the Earth's distant past. And it got people thinking, well, if there were glaciers at sea level near the equator, it led them to believe that the world's oceans must be completely covered in ice cover. And we call this ice cover a sea glacier. So sea glaciers don't presently exist on the Earth, and because they're incapable of being produced in today's climate, but they differ from things that you might know, like sea ice. Sea ice is grown locally and doesn't flow, whereas sea glaciers flow. And ice shelves you might be familiar with because they flow and they cover the ocean, but they depend on their input from continental landmass, whereas sea glaciers are self-sustaining. So they're self-sustaining thick ice masses that deform and flow under their own weight. And they have covered this Snowball Earth. So I said that it happened during the distant past. These events are thought to have occurred during the Neoproterozoic, and so we are pretty confident that 2 of these events happened where the Earth's oceans were completely frozen over during the Neoproterozoic, and they each lasted for about millions to tens of millions of years. So the Neoproterozoic is a time about 600 to 800 million years ago, and it predates a lot of things that we're familiar with. It predates land plants, so any kind of plants that would be on land. Most animals, there were a few like kinds of sponges that existed, but really it was a pretty primitive form of life that existed on Snowball Earth. So you might ask, okay, it's a pretty crazy claim that the Earth's oceans were completely frozen over. What's the evidence for this? Well, one thing that we have is what are called drop stones. This is a drop stone. So you can see here, this is a rock that has deformed these layers that surround it, okay? And so this drop stone fell from an iceberg and deformed this sediment and has since become a rock, okay? So drop stones work like this. Glaciers that form on land, they'll carry with them rock that they've eroded, and as that ice reaches the ocean, it begins to float, and the floating ice shelf will eventually produce icebergs. And as these icebergs melt, the debris that's being carried with that ice will melt out and drop these stones into the soft ground and drop it into the soft ground. So if you were to go to places like around the coast of Antarctica or Greenland, you would find drop stones being actively dropped under icebergs there. So we see this drop stone and we say, okay, there must have been, this is like an ocean floor, and there must have been glaciers nearby where this was dropped. But the real question is, how do we know that this glacier, but we have glaciers today, but how do we know that these glaciers imply the Snowball Earth? Well, really the implication comes from the fact that these glaciers were at near the equator, okay? And here's how we know this, or here's how we're able to demonstrate this, is that you can see there's layers in here, and those layers contain magnetic minerals. And so the magnetic minerals will align themselves preferentially to the Earth's magnetic field. So if you're standing on the North Pole or the South Pole, the magnetic field will point straight up or straight down. But if you're standing near the equator, near the tropics, the magnetic field will be horizontal, or like this. And so when we're able to measure the magnetic field in these minerals, we're able to measure horizontal magnetic fields that imply that this was near the tropics or the equator. So what scientists have assumed is that if you have glaciers at sea level near the equator, you must have glaciers everywhere on the planet's oceans. So how do we get into this crazy state, okay? Okay, so first there's the sun, which during the Neoproterozoic, about 600 million years ago, the sun was dimmer. So it was a little bit less active, by about 6%, so not a major thing. But the other thing that keeps the planet warm is carbon dioxide in the Earth's atmosphere. So if there's a way to remove a lot of carbon dioxide in the atmosphere, then you can make the planet colder. And so a way of doing that is by what these are called, this is like a basalt flow. And so what we think, the leading hypothesis is that large igneous provenances, which are massive amounts of basalt flows, came out and extruded all at once. Now this basalt is very chemically unstable, and it reacts with the carbon dioxide in the atmosphere, and that carbon dioxide is pulled out of the atmosphere. And if that rock that it produces gets buried and removed, then that carbon dioxide has no way of getting back into the atmosphere. So the Earth's atmosphere will lower its content in CO2 over time, and it will become colder. So I want to introduce you to this concept called the ice albedo feedback. A very interesting property of ice is that ice is formed from water, as you know, but water is relatively dark compared to ice. So ice is very bright. So if you can imagine a planet here just made of water, you might have an ice cap here where the sun's rays can reflect off of. But if you are able to cool the planet slightly, you're going to expand that ice cap. And as you expand that ice cap, more light gets reflected back out into space. And it's not being used to warm the planet. So therefore, the planet gets colder, at which point the planet will reach. And so there are some stable positions here, but at some point, the whole planet will just become a shell of ice. So looking like this snowball here. So, okay, so that's a pretty outrageous claim, but how would you ever get out of a snowball Earth? If the oceans were completely frozen over, how would you get out of that? Well, the answer kind of also lies with volcanism. So volcanoes are relatively unaffected by this process of having ice everywhere. So they will continue to erupt their gas and ash. And one of the gases that volcanoes release is carbon dioxide. And so over the millions of years that these snowball Earth events last, these volcanoes will degas and build up carbon dioxide in the Earth's atmosphere. So, okay, so if we have all this carbon dioxide in the atmosphere and it slowly grows out of it slowly warms the planet, one consequence is that as soon as we're able to start melting the ice near the equator, and as soon as we're able to get rid of that bright ice near the equator, the whole planet will warm up very, very rapidly, within thousands to tens of thousands years, we think. And so there's an interesting geologic record of this very same phenomenon. This is what's called a cap carbonate deposit. And here on the top, we have carbonate, and here on the bottom is diamictite. And there's a transition between, of which is conformable with time, meaning there's no time between these two events. And diamictite is formed from glaciers in very cold conditions. However, carbonate forms in warm seaways. So how do you go from a very cold condition to a very warm condition all at once, just nearly instantaneously? It's by getting out of the snowball in just a few thousand years. So once the snowball destabilizes, the oceans are no longer cold and full of glaciers. They go to very tropical conditions, which will persist for many millions of years. So it's favorable for carbonate deposition. And we don't just see this in this one place in Namibia. We can find this sequence globally during these Neoproterozoic, during the same time period, wherever we look for them, okay? And there's another piece to this. There's the Snowball Earth climate models, okay? So I'm going to tell a little story about two climate scientists, Budko and Sellers, who independently in the year 1969 both published works basically explaining this same phenomenon, but not from a geologic evidence perspective, but based on simple energy balance models of the Earth. And so what they found is that because of this ice albedo feedback, that we're able, remember, just to remind you, the ice albedo feedback is that when ice is bright, and when you increase this ice line, you're reflecting more energy back out to space, and so the planet will cool, and eventually you reach this state of a complete snowball. So let me explain this graph here. On this, we have carbon dioxide in the atmosphere. So more carbon dioxide means warmer conditions. And we can think of that equivalently as solar flux, so the amount of solar radiation that's reaching the Earth. And so we could have the solar output increase or decrease too. So those are equivalent. So here we are, this yellow dot, present day conditions, solar flux of 1.0, and then one of our present level of CO2. Neoproterozoic conditions during the Snowball Earth were the sun was thought to be about here, but if the sun's output, but if we lower the carbon dioxide, what they found is that once the ice line, so once the ice reached about 30 degrees in latitude, the oceans would be completely frozen over. The ice would just completely collapse in on the equator, and we'd reach this all ice state. And then what else they found is once you reach this all ice state, it doesn't, you can start adding carbon dioxide back in the atmosphere, and we're not going to go back to this point again where we're up to where the ice line is at 30. No, you have to raise the carbon dioxide and stay on this line and have the carbon dioxide be about over 500 times the present day concentration, and then it finally gets warm enough to melt melt the equator, and then nearly instantaneously go to this no ice condition. And it isn't until you can draw it back down that you can reach these kind of states where you have some ice. So there's 3 states here: all ice, no ice, and the state where we have some ice. So this is cool because it kind of confirms what we saw earlier with that cap carbonate. So going from this all ice to no ice really instantaneously in that geologic record. So we have models that have kind of predicted the geologic sequence, and we're able to see that. So this is kind of a vision of Snowball Earth. It's like this idea that the Earth was this kind of frozen over ice ball everywhere. And so let me explain to you a little bit more about what we're able to understand about Snowball Earth, given some constraints here. So like the present day Earth, the Snowball Earth would have been colder at the poles and warmer at the tropics, still below freezing, but relatively warm. And because of that, the ice that is over the ocean will be thinner in the warmer areas and thicker over the colder areas, because ice can grow thicker if it's colder, and ice can't grow as thick when it's warmer. So what that does is it means that you have thick ice at the poles and thin ice at the equator. And what that does is it drives the ice to flow from the poles to the tropics, to the equator. And so the ice is flowing equatorially, or toward the equator. And this flow of ice is balanced by a hydrologic cycle. And so at the poles we have accumulation, so we have snowfall and ice freeze-on. And near the equator we have sublimation. And sublimation is just the process by which ice goes directly from its solid state to its vapor state. So let me talk a little bit about the role of life on Snowball Earth. So I've told you that the Neoproterozoic predates land plants and most animals. But photosynthetic plants and simple algae eukaryotes were present prior to and subsequent the Snowball Earth events. So we've inferred, because we can see them in the geologic record before and after, that they must have persisted during these events. And because if they hadn't, that would have meant that life would have had to have kind of re-evolved into that state. And that's not really clear if that could even happen. But this requires that you have liquid water at the surface. So liquid water where these organisms can take advantage of the light that they need. They're photosynthetic, they need light. So this is a picture of this algae, but I like to think of the algae as this now famous little green man. So the real bigger question that I'm trying to ask is the survival of photosynthetic life inconsistent with the Snowball Earth hypothesis, the hypothesis that all of the oceans were frozen over? Well, let me just go through some places where I don't think life survived, where life wouldn't have been able to survive on this planet. It wouldn't have been able to survive in snow, because it would have always been, even though there's light available, it never would have gotten liquid water there, because it's always too cold. There are deep sea vents deep under the ocean. Microbes live there today, and microbes would have lived in these environments during Snowball Earth events, but not photosynthetic organisms, because they need light to survive, not the chemicals that would have been supplied there. Lakes wouldn't have been able to have provided a refuge for these organisms, because if they're in a zone of snowfall, then the lakes would completely have frozen over. But if they're in a zone of sublimation, then they would have eventually dried up over this million-year-long time period, multi-million-year-long time period. So my question, the question that I have addressed here is, were narrow marine embayments viable refugia for these photosynthetic organisms during the Snowball Earth events? And let me explain to you what a narrow marine embayment is, and this theory. Okay, so we have this vision of this planet, the snowball, with sublimation at the tropics and warmer conditions here. And what I would suggest is that narrow marine embayments, like the ones seen here, could provide a refuge for these organisms, because ice might be able to be sublimated away before it can penetrate into these embayments. And so I have one here on this thing, but you could imagine many of them. They could just be in lots of different places. We don't know the paleogeography of during the Neoproterozoic very well. And so we kind of have to hypothesize a little bit about their existence. So when I say narrow marine embayments, the analog that I like to use is the modern day Red Sea. Because the modern day Red Sea is connected to the ocean, it's long and it's narrow, and it's created by a process called continental rifting, where plate tectonics will rift continents apart. And this is attractive because that process is controlled by workings deep within the Earth that wouldn't have been affected by snow layer or the Snowball Earth conditions that are on the Earth's surface. So they're happening much deeper. So let me explain to you why I think this is a reasonable idea. So I have two pictures here. The top is a profile view, a side view, and the bottom is a map view, and they're of the same thing. And so we have a sea glacier here that's in the ocean, covering the ocean. And if the sea glacier is very thick, light from the sun can't penetrate through it. It's too thick. It gets absorbed, and photosynthetic organisms can't survive. But as ice flows into this narrow marine embayment, it's going to experience resistance at its sidewalls. And if we're in a zone of net sublimation like we have near the equator, then that ice, as it's being resisted, is also going to be removed. So it's transferring into vapor. It's vaporizing away. And so if this channel is long enough, then eventually this sea glacier will reach zero thickness. There'll be none of it left. It'll just all have been sublimated away. And maybe you could have a lake there at the end where these marine organisms, these photosynthetic algae, may have survived. So really, to answer this question from this perspective, the question you really need to ask is, how far can a sea glacier move into a channel? So let's ask that question. So how far can a sea glacier penetrate into a channel? And I'm going to start with a hypothesis. I'm just going to say sublimation rates, which is the rate you're removing the ice, vaporizing the ice, are so small during the Snowball Earth events that channels would have to have been unrealistically large and narrow to keep these sea glaciers out. And so how are we going to address this? Well, we can use a model of ice flow, coupled to a mass conservation equation to keep track of the ice vaporization rate, to determine sea glacier penetration into that channel. So let me step back and talk a little bit about how ice flows and the mechanics a little bit. So if we have here's a picture, a cartoon of a glacier, where we have an accumulation zone, which is where snowfall exceeds the amount that's removed from ablation, melting, sublimation, things like that. And then we have an ablation zone, where there's more ice being removed than there is being deposited. More snow is melting or being sublimated away than is being deposited every year. So in a traditional glacier, the ice will, the ice will flow from the accumulation zone to the ablation zone. So why is that really? Well, the physics is pretty simple. So imagine you have this slanted surface, and at point 1, you have extra pressure compared to point 2, because there's more stuff above it. And so what that does is creates a stress gradient. So there's a gradient in the stress here, and ice will deform in response to that stress, so it will flow. And we call that stress the gravitational driving stress. And that stress is resisted at the boundaries by resistive stresses. So that is what slows the glacier down. This speeds the glacier up, this slows it down. So let's talk a little bit about glacier flow. These resistive stresses come in 3 different basic flavors. You have vertical shearing, which is caused by traction on the glacier's bed. So if the glacier is moving down this tunnel, there's going to be traction here. You have lateral shearing, which is caused by traction along the sidewalls. And then you have longitudinal stretching, which is caused by the stretching or the compression of the ice itself. Luckily, if we're considering a sea glacier moving into a channel, if the sea glacier is floating, water doesn't provide any traction. And so we don't have to take into account the vertical shearing, because if it exists, it's very small. So we want to know how far the sea glacier penetrates into a channel, and we need to take into account this longitudinal stretching, this lateral shearing, okay? So just how far does a sea glacier go? Okay, we have these 3 stresses. So in this first model that I'm going to explain to you now, which is the first work that I've done, we just looked at lateral shearing. And so we considered a sea glacier of some thickness h that we set when it moves into the channel, and it has some uniform width. Okay, so the sea glacier is moving into a square or a rectangular channel, and we want to know how far does it penetrate. We want to calculate L. So we assume lateral shearing only. We assume it's in steady state. We're able to specify a sublimation rate and temperature, and we have a fixed width and entrance thickness. And with this, we're able to calculate a penetration distance, the velocity across the channel, and the thickness gradient. So here's an example. So I'm going to calculate the sea glacier penetration to a channel L. So remember, we have this channel. This is looking up. This is like a map view. So imagine this is the entrance of the channel, and this is the width here, W. And we want to know how far does the ice travel. And so for this example, we have 650 meters upstream thickness. We want to know how far the ice travels before h equals 0. And for reference, the Red Sea is our kind of analog. So the Red Sea has this 200-kilometer width, and it penetrates 1,300 kilometers. And so what I'm able to do is, for different combinations of sublimation rate and surface air temperature, I'm able to calculate how far this sea glacier would penetrate into a channel. And so what I have here, these contours are in hundreds of kilometers. And so this 13 one that's dashed is the length, 1,300 kilometers of the Red Sea. And so what that means is that if you pick a combination of sublimation rate and temperature that lies to the left of this line, then, for example, if it lied on this line, then the sea glacier would only penetrate 1,200 kilometers, not the 1,300 kilometers of the Red Sea. So it would incompletely penetrate that. And that might leave a little refuge or lake for these photosynthetic organisms to survive. However, if you were on these set of climate conditions, to the right side of this line, then a Red Sea would be completely penetrated, because this sea glacier could penetrate 1,800 kilometers, longer than the Red Sea. So photosynthetic organisms wouldn't survive there. So I'm able to demonstrate that that you can keep ice out of this kind of channel given some range of climate conditions, although they are fairly restrictive. So let's just talk a little bit about this, an interesting question that came up in the review process for this paper. Question was, do these inland seas, do these places, do they get overridden by sea glaciers as the snowball warms? So the idea is that as the snowball warms, gradually getting out of the Snowball Earth state, the ice will soften, and the sea glacier will therefore be able to penetrate further into the channel, and it might destroy the refugium. But there's a competing effect, which is that as you warm the planet, you also increase the sublimation rate. So what I've done is I've calculated the changes in the sublimation rate and the ice softness with warming temperatures of the snowball. And so to calculate this, I just started at a low temperature, and I looked at the increase in sublimation rate and the increase in ice softness. So sublimation rate going from -50 to 0 Celsius increases by about a factor of 150, whereas the ice softness only increases by about a factor of 20. And the overall effect of this is that as you warm from this cold condition, you don't increase the size of the sea glacier, you actually decrease it, because sublimation wins out. So okay, I was able to demonstrate that you could keep this thing incompletely penetrated under certain climate conditions. But I also said, like, well, I had this kind of narrow rectangular channel, right? But one thing I noticed about the Red Sea and a lot of seas and a lot of marine embayments is that they have these narrow entrances, okay? And so I asked the question, do narrow entrances matter? How does that affect our result? So now I want to calculate how far a sea glacier can penetrate into a channel. But for this, I'm using a more sophisticated model, where I'm able also to calculate the longitudinal stress as well. So I have the same geometry, but I'm able to calculate longitudinal stretching and lateral shearing under these same assumptions. And with this, I'm able to calculate the penetration distance and the velocity field in 2D. And the full thickness field. So here's kind of a map view of this. So imagine a sea glacier in the ocean coming to the channel that has some width here. So here's the sea glacier, the channel, and the entrance width, and then you're surrounded by land. And I can adjust the temperature, the sublimation rate, and the entrance width in my model. And with that, I am able to calculate the thickness field of the penetrating sea glacier. So these contours are in in meters, and this shows the thickness, and the arrows indicate the velocity. And so you can see here that this sea glacier is able to penetrate about 300 kilometers here, and before it terminates and maybe leaves some water here, a lake, at the terminus of it. The other thing that we saw that was really interesting that we didn't expect is that we have these zones of really thin ice. Notice that there's very thin ice immediately adjacent to the entrance. And the reason that is because ice has a very difficult time kind of turning around and getting here, because ice is going to flow straight through here and kind of doesn't even want to go there. Some ice does get there, but it thins out really relatively, it thins out quite a bit. So keep that in mind for the next section when I show you that research. So again, we want to calculate the sea glacier penetration, and we have the surface air temperature and the sublimation rate. And again, we have the same setup where we have some width, but we also have an entrance that we can adjust here, and we want to calculate the distance we travel before we reach zero thickness. And we have an upstream ice thickness is the same, and the Red Sea dimensions haven't changed either. So yeah, so here's the example you saw before. But if we use an entrance that's about twice the size of the entrance of the Red Sea, we're able to expand this set of climate conditions that allow for incomplete penetration further, okay? So meaning that anything to the left of this blue line would allow for incomplete penetration of the Red Sea, whereas anything to the right would mean complete penetration. So my results for the sea glacier flow model is that I'm able to adjust the temperature, the sublimation rate, and the entrance width in my model. And what we found is that inland seas are capable of keeping out sea glaciers under certain climate conditions. And that smaller entrance widths expand that range of conditions. And that you're capable of producing thin ice near the entrances here. Okay, so we have this thin ice zones. So let's come back to this idea. So one other thing is that we thought of was that, well, the Red Sea isn't just a rectangular channel with some narrow entrance. It has obstructions in it. So we wanted to know, do obstructions matter? So what we did is we modified our model, and this is work I did with an undergraduate student, Bets Mazzarano, who helped perform these experiments. And so what we did was put in promontories into our model, and we wanted to know, if we adjust the size of this promontory, do we have an effect on the sea glacier penetration? And it turns out that as we increase the size of this promontory, we can decrease the penetration length of the sea glacier. So that also modulates it, kind of suggesting that our initial work that we had done was kind of an upper limit for sea glacier penetration. So the other thing that I want to talk about is ice shadows. So we had this idea that maybe ice that's flowing around this promontory, maybe isn't able to fill in the far side of this around this promontory. Much like we saw that ice had a hard time getting into these areas immediately adjacent to the entrance, we asked, does that happen there on these sides of the promontories? So we called these things ice shadows, these places where the ice would have been shadowed by land. And so before I start talking about this too much, I wanted to show you a cool picture and tell a story about these Waddell seals. These are adorable seals that live on White Island. So White Island is this island. It's the white one, and it's right next to Black Island here. And they are in the Ross Sea. So the Ross ice shelf is flowing in this direction. And what happens is that ice, as it's flowing around here, is thin relative here, or is thin on this section where it has a hard time getting to relative to here. And what exists there is a crack in the ice shelf that is a tidally generated crack that is able to be opened continuously. And that crack allows for these Waddell seals to swim underneath the ocean and hunt, and then also come up to shore where they can rest. And this is a refuge for these organisms. So they stay there in this place because because this island provides a blockage to ice flow there, so the ice is thin enough that it can generate that crack. And then another kind of analogous example that we have is this glacier as it flows around Finger Mountain. So this is a grounded glacier. This isn't a floating one, but it's sitting on land. And it kind of has the same effect. So this glacier flows here around Finger Mountain, which is this mountain here, and turns around, and it kind of incompletely penetrates into this valley. And so maybe not surprisingly, this glacier is called Turnabout Glacier because it turns around, does a 180, and you notice that the valley continues here, but it can't penetrate into that valley completely. So it has a difficult time. It's completely removed. This acts as an ice shadow. So what we were able to do is ask the question, is the ice thin enough in this downstream section here? So this little box, we want to know, is there thin ice there so that you could have a refuge for organisms? And what we found out is that as you increase the promontory size, you're increasing the amount of sea glacier free area. However, our model has a high limit of 50 meters for vertical resolution. So we can't distinguish any of the sea glacier free areas from anything less than 50 meters. But because we're getting such areas, we think it's likely that we have some area that's free of the sea glacier. So thin ice that's significantly thinner than that. Okay. So I'm going to come back to this initial kind of cartoon I showed you of this marine embayment hypothesis. And I wanted to demonstrate that maybe marine embayments were viable refuges for these organisms. And so to do that, you have to demonstrate that a sea glacier can't penetrate into that channel. And with my PhD work, I've been able to demonstrate that. And a few other questions will come to mind and looking at this, and I just wanted to address those. One is, would land be covered in glaciers? So if you could imagine that this land, instead of being barren, is covered in glaciers, then it might just fill in that lake. And it doesn't matter if the sea glacier can't get to it because the land glaciers could. And then even if that didn't happen, would sea ice grow locally? So would cold conditions make sea ice just thick sea ice that grows in place because of cold conditions? Would that grow over the refugium and prohibit that? So here's kind of our current vision of Snowball Earth, is this ice-covered planet where there's ice everywhere. But I kind of want to argue as maybe an alternative hypothesis to this, and argue that maybe some of the land isn't covered in glaciers. So this is some work from Dorian Abbott and Raymond Pierre-Humbert that they published in 2010. And what they have here is a climate model. So this is latitude and longitude. This is a map. And what they have here is an ocean-covered world. And they've inserted a single rectangular continent here in the middle. And they forced this into Snowball Earth climate conditions. And they were able to calculate temperatures. And what you can find is that the temperatures are quite a bit higher over this land that is barren. And the other thing that they found is that that they were able to calculate the sublimation rate and the accumulation rate zonally average. So what this means is that at latitudes where we're on the right, where this green line is on the right side of this dividing line, then we have net snowfall. But on the places where it's not, so where it's to the left side of this line, then we have net loss. So that implies that places between here and here would be relatively dry. And so there's relatively few places on this continent where, so that part of this continent lies in the accumulation zone where glaciers could build up, but they probably would be sublimated away before they could reach this equator. And so for this particular model, they have a pretty wide sublimation zone because of their inclusion of this continent, but all Snowball Earth models have a zone of net sublimation, the most conservative of which usually run from about 10 degrees north to 10 degrees south. And so any small continent that's centered on the equator would probably remain dry. So equatorial continents may be free of glaciers, and we need these to be in the zone of net sublimation anyway for the sea glacier model to work. So we're kind of already built in this assumption. So the next question is, would sea ice grow over this refugium? Well, I could talk about that real quick. So remember that if we can keep it free of glaciers, then we'd have bare land. And this low albedo land, which low albedo just means it's better at absorbing the light, will absorb heat. And that heat will be able to warm this air of the lake. And so the question is, what is the thickness of that sea ice that grows? Are you able to keep that sea ice thin enough? So if we have low albedo land, land may provide the warmth that's needed to keep that sea ice thin. So we have this vision of Snowball Earth, and I kind of just want to say, what do we know? We know that photosynthetic life existed before and after these Snowball Earth events, so we think that it survived these events somehow. And we think that we had complete ocean cover of the planet. And we also know that marine embayments, so the first class of refugia, that are being, for this kind of condition where we have a completely ice-covered oceans, for a snowball to be studied in detail. So no one's actually studied the refugia on this kind of vision of this planet. And I've been able to demonstrate that marine embayments can prevent sea glacier invasion, and that marine embayments can also probably not get frozen over or invaded by land glaciers. So if we have this vision of this snowball, which is this completely ice-covered planet, I think we need to transition out of that vision to think of a planet where we don't have this complete ice cover. We have an ice-covered ocean that's complete, but we're going to have some bare land over the equatorial latitude. And we're not sure what the width of that is, but there's going to be some zone where we have to have sublimation. And so I just wanted to end on a final thought, which is when I was young, I thought about my stuff I saw and the universe around me, and I thought that, what else is out there in the universe? And I think that Snowball Earth is such a cool thing because it allows us to look in this Earth's distant past and able to explore how life could survive. But if we think about the hundreds and hundreds of exoplanets, the new planets outside of our solar system that have just been discovered in the last decade, we might see planets out there that look like Snowball Earth, and we have to wonder, is there life on those planets as well? All right, thank you very much, and I'll take any questions. Ed will be my moderator.
Al.
We should say now, in fact, we should set it at the beginning of talk about why all ablation is assigned to sublimation and one melting.
Well, you'd have to have temperatures above freezing, and certainly in some of the warmer conditions, you would have seasonal melting. Yeah, and you could also have submarine melting, and that's another factor. And I didn't take that into account, and because the reason is that the climate models where they've coupled an ocean and atmospheric model to an ice-covered world, they've been able to demonstrate that in the places where there's sublimation, there's also a same order of magnitude melting. So we see generally for the aquaplanets, we're able to see melting where there's sublimation wherever there's sublimation on the surface, there's submarine melting. And I wanted this work to kind of be an upper bound. So if I just prescribed a melting, then the sea glaciers wouldn't penetrate as much. So if it's melting, it's probably not going to penetrate as much. But I kind of wanted to give the best argument to the sea glacier penetrating to begin. So that's kind of, it's not something that we didn't think about. It's just something that we didn't have a good handle on, and we thought maybe that would be, it could only help the case, basically. So, yeah.
So how does your model explain all the diamond heights and rock stones if we don't have land ice and our sea glaciers aren't?
Yeah, so I think you could still have, so I think you could still have, so I think you could still have places like the coast of Alaska where you have large, mountains very...
They're low latitude, right?
Yeah.
Agreed that these sites are low latitude.
Yeah. So I think that coastal places where you have mountains where you could seed glaciation there, those mountains could probably have glaciers that reach sea level. But I think that you can argue that at least some, especially interior sites, might not have those conditions.
Kristen and then Daryl.
How constant is the geometry of the rift valley over the time scale?
Yeah, that's a good question. Yeah, it does matter. It would get wider, and so it would widen it, you know, maybe a few centimeters a year, but over 1 million years, that's kilometers. And so, yeah, those would widen over time. But, yeah, I think that would be something that would need to be considered. But I think there are also ways to kind of generate these kind of features that could be in absence of a rift valley, but I think, yeah, it's a good question, and I don't know if I have a great answer for you, but I think that as you widened it, you would increase the penetration, but you might also have some other effects that might restore that. So,
Daryl.
Adam, what is the work on the ground on the geologic record of Snowball Earth in Namibia, Death Valley, Canada, shown about the possibility of marine embayments? I mean, a lot of work has gone on studying the facies of these deposits. The Hoffmans or the McDonalds said, yes, these look like they were restricted, needing help you.
yeah. You know, I have chatted with Paul Hoffman and Francis McDonald about this, and I don't know if they have any evidence to directly support this, but I don't think that they disbelieve it based on the geologic record. It's a little bit difficult for me to wear the geologist hat here, but it's you know, and I did talk with someone at GSA who thinks maybe they could see this environment, but in Death Valley deposits. But yeah, I mean, it's the kind of thing where I would be curious to know what to look for. Like, what would be like is there a geologic thing that would, a geologic silver bullet that might say, oh, this is like this environment. But I think it's also, yeah, it's cool because I like this Snowball Earth hypothesis because I feel like models and geology are kind of informing each other to make this. And it's really interesting when those can work in tandem. So,
What are the chances of finding a rift valley 800 million years later?
One of the early ideas in Death Valley is that right in Troxel there was an Alakachev, it was a failed rift, and that came from geologic studies on the ground and thinking about pre-Cambrian tectonics. So I think the geologic record might be promising.
okay.
Some things are preserved.
Excellent.
Yeah.
Similar to Kristen's about the rift valleys being stable, is the climate going to be stable enough that you would have these kind of lakes persisting for?
Yeah, so you need some way to resupply the water. So if it has a connection to the ocean, that would be obvious. But yeah, and you would expect, and so remember when I did that sea-glacier penetration model, so the temperatures are going to warm up slowly over the course of until you reach that kind of destabilization point, then everything gets really warm really quick. Yeah, I mean, you'd certainly have orbital forcings and diurnal forcings and annual forcings, but and those could play a major factor, but because you could have things like seasonal melt or, you know, melt during warm periods, but yeah.
What's the global temperature swing in Milankovitch 100,000-year cycles roughly?
The global?
Yeah, how much is the Earth warm or cool?
I don't think it's very much as a global. I mean, I think that over certain locations it makes a big difference, like particularly Canada and where you find the Laurentide and the Fendoscandian ice sheets. But yeah, I don't think globally it would make a huge impact.
Yeah, some people here may know.
Yeah.
So maybe Steve has
5 degrees? Okay. Globally? Okay. That's more than I would have thought, but...
And you're talking about equatorial, which could be less,
Yeah.
less than the average. So you can compare that to your difference in getting into a snowball compared to today. How important would be Blankovich sort of cycling?
Oh, to get into a snowball? Or...
If you've changed from modern day into a snowball condition,
Mm-hmm.
then you're going to add 5-degree flutter on it. Is that going to be critical?
I mean, it could be in some environments, certainly in the equatorial regions, yeah, because the stuff that Abbott and Pierre Humbert published was mean annual temperatures of I think up to in the -10 to -20, so that would have a big impact, especially since seasonal is probably enough to get up melting even in their model as is. So, yeah.
Okay. I better not be asking the question. Charlotte?
Well, the Red Sea is still opening up, and it started out about 30 million years ago, 25 million years ago. So it hasn't changed its dimensions hugely.
Oh, okay.
So you can have that as a model. But the other thing that's quite interesting is there's a lot of hydrothermal water entering into that,
Mm-hmm.
being the bottom of the Red Sea relatively warm.
Yeah. I think that would definitely help this as a potential refugium because it would keep things warmer and keep sea ice thinner if you increase the geothermal flux, increase...
Pretty high geothermal flux. And if it's a basin is being held together, there's a lot of sub-fractures that are also bringing warm water up that might help with the piping.
Yeah. Yeah, I've thought about that. If you could have if you were to close off this seaway with the sea glacier, if you were in this kind of rifting zone, would you be able to have groundwater flow through this kind of? And I kind of imagine like basaltic or things like that, like pillow basalts that might flow there that are relatively porous.
Looking at the bottom of the Red Sea today, that's what you see.
Okay, yeah.
Parallel to the rift, the old fracture zones are still hydrothermal vents.
Yeah.
I'm curious how sensitive the penetration distance is compared to the thickness of the glacier as it comes in.
Yeah. So it's linear. Yeah. So at least for the simple model we did. Yeah. Yep. That's easy.
Yeah, with regard to Jody's question, I guess she's not here anymore, but
Yeah, she had to teach.
about the drop stone you showed, could that drop stone, instead of coming from land, could it have come from a sea glacier, grounded on shallow continental shelf, eroding the continental shelf, and collecting a rock that way, or did it have to come from land?
I think that you could, I think that if a sea glacier were to lightly ground at some latitude, it could probably carry with it.
Even in the tropics.
Or even in the, yeah.
Grounded on.
It has to get frozen on and then get transported before it melts away though. So it can't spend too much time in the melting zone. Yeah, so that's the thing. Because if we assume that it's melting somewhere in the tropics, then, if it gets eroded right at the, yeah, exactly. But if it could come from further upstream, that's certainly a possibility. Yeah.
The Neoproterozoic has a lot of drop stones.
I wanted to add to Kat's question. So the thickness that you use, the 650,
Yeah.
where do you come up with an estimate
Yeah.
of sea glacier thickness?
Yeah.
If it's linear, then say it's like 1,200 meters, you're going 2,400 kilometers.
Yep. So there have been a few models of sea glacier thickness over the ocean for like an aquaplanet model. So I kind of just use that as like a basis for like the equatorial thickness of the sea glacier. And so it's a little bit different thickness depending on what model you pick, and I think 650 meters is a little bit on the low end, but I think, probably 900 would be probably on the high end. So, so it's not a huge, it's not going to be, I don't think it'll be triple or double or anything, so.
Is there any way you can get any sort of geologic evidence to figure out besides the models, but
Oh, that's why I got to talk to Daryl. Yeah. No, I think that's a great question. So.
Yeah, I was wondering if you have the sea glacier flowing down towards the equator,
Mhm.
having ablation as you're going down, would you get blue ice? Barren of.
Yep. Yeah, you might get blue ice, but you also might get a salt crust as well. So if a sea glacier were to incorporate seawater, and that were to be able to and that would incorporate some brine, and if that were to and the sublimation might transport that brine to the surface, you might. Yeah, you might get marine ice, but you might also get this kind of layer of salt-covered ice too, which is that's the work of Regina and yeah. So studying like what that effect would be, because that's a big difference, because the blue ice, that marine ice, is going to be very dark and be able to absorb more light. But if you have a salt layer on top of that, then you might have additional albedo from that. So.
Did you do any experiments where you added basal melt or not?
No, because I didn't add any basal melt, because it's just another like factor in the mass balance term. So I could have added it, but I wanted to give the sea glacier the best chance of penetrating it. So I think that if you added basal melt, it would just diminish that penetration. And yeah, they're like 2 to 20 millimeters. So yeah, so a few centimeters would be on the high end. Yeah. Yeah.
Putting a lid on it, it seems like there's not going to be a lot of circulation coming out of there, so it seems like melting would be really important.
Yeah, I mean, I think it is. I mean, I think it would be in effect, but I kind of just took the position of, well, let's just say that doesn't exist to see if it what the parameters are, and if we can say that it happens here, then we know if we take that into account, then we can reduce that penetration.
Any other questions for Adam?
Well, that's a logical, I guess, question. So would you say that the whole marine embayment as a refugium is kind of stamp solved, or do you have anything left to do on it as future work?
No, I would say it's not stamp solved, because you still have to demonstrate that sea ice that's grown locally wouldn't get too thick to allow for, so it wouldn't get so thick that you couldn't have light penetration below. I wouldn't say it's stamp solved, but I would say that I've made the first steps in doing that, and I've made the most, yeah, like I've outlined like, here's how you would solve this problem. Yeah.
So Adam, could these bugs have just gone into hibernation?
People have suggested it, and I think that I've heard more biologists kind of say that, but when this it used to be that that biologists were the ones people coming out about the Snowball Earth hypothesis, because they said, well, we have this photosynthetic organisms before and after, they probably survived, we don't think they re-evolved, and then there's not an environment for it, so is that demonstrating that the hard snowball didn't exist? And so, yeah, I mean, and I think more people have said that, and like someone has, I saw a paper the other day about photosynthetic microbes that might survive near deep sea vents, and I was like, oh my gosh, okay. But I don't think they're the same kind as this that we found, and there's been a number of things. But also remember, I guess something I didn't say is that one thing that's attractive about this as a refugia for these organisms is that they can be large. And so the idea is that if you have a small refugia, you might not be able to repopulate. It might get destroyed in the process. But if you're able to have few large refugias, then yeah, you might be able to, it makes sense you'd be able to repopulate the planet. So, yeah.
So you could have sea ice, but how deep can light penetrate through? Or what thickness?
It really depends on the optical properties of the ice. So some ice is very clear, and you could probably penetrate through maybe over 30 meters of that if it's very clear. But if it contains a lot of bubbles, it's going to scatter, and you would need it to be much thinner. So it really depends on that aspect, yeah.
What do you think the biggest argument is against there being just a narrow band in the equator of the ocean? Because I don't know how accurate paleomagnetism data is. Like, can you pinpoint?
Yeah, I think, I mean, people have generated models which have done that, but they've only been able to do them for aquaplanets, and when they've tried to do them on planets with continents, it turns out that that's a critical factor, and they're not able to kind of create those bands of open water. Plus, they know that most of the continents at the time were probably closer to the equator than they are today, so it probably does matter. And so I just haven't been able to see, you know, people have created models where they're able to get these, but they have to like seed them there, and they're not able to get to them from like a kind of a state. And so it's difficult to demonstrate that it's stable, or maybe that's not difficult to demonstrate that it's stable on an aquaplanet, but that you can even get to that state on an aquaplanet given some forcing from a non-state of that. Because it might be a state that you could just never really achieve. So, yeah.
Well, would the carbonate be evidence against the water depth? The fact that you did have to, would the carbon dioxide have built up that much? If you had a water depth, it could then grow as it got warmer.
Yeah, so I think that you could saturate, I mean, you could increase the carbon dioxide in the ocean too. And, you know, you might have some coupling between the ocean and the atmosphere. Even with a hard snowball, even if there's like some, like this kind of lake idea, you might have some exchange there. So I think that the reason that the carbonates form at the end of the snowball is not because now all of a sudden there's more carbon dioxide in the water. I think it's because the water is warmer now, and then it's favorable for that carbonate production.
Okay, thanks very much. We're going to move
All right.
to closed session now, so
Thank you. Okay.
Good luck. Thanks, bud. Great talk. Thank you. Thank you.